So in this video we'll be talking about nuclear fission, and the definition of nuclear fission is if you take a large radioactive nuclide, say for example uranium 235, which is an isotope of uranium. If you take that isotope of uranium, you can split it into two smaller fragments, and those two smaller fragments will usually end up as other nuclei. So to kind of introduce this topic, we need to talk about the amount of energy that's contained inside the nucleus. So there's a lot of information on the board, so let's just maybe start right here. Well, actually, let's start right here. So whether or not you learned about this in physics last year, but this is a very famous equation. It's Einstein's big contribution to science, or one of them at least. But what this equation means, E equals mc squared, is that energy and mass have a relationship. So energy is equal to the mass multiplied by the speed of light squared. So E equals mc squared. So we'll go back to look at this equation in a second. But for right now, let's look at how much energy is inside the nucleus. And to do that, we need to look at how much mass is inside the nucleus. So if we looked at oxygen-16, which is a regular, stable isotope of oxygen, and we're going to look at the mass of the nucleus. And so inside the nucleus of oxygen, you've got 8 protons and 8 neutrons. Excuse me, the mass of a proton and the mass of a neutron is equal. It's 1.67492 times 10 to the power of minus 24 grams, which is a really, really small amount. These two are identical, and this is why we use scientific notation, which we learned about a long time ago. You take the 8 protons multiplied by the mass, and then you add that to 8 times the number of neutrons, and you get this number. So this would be the theoretical number, but in actual fact the value that has been measured is actually 2.65535 times 10 to the minus 23, which is a little bit different from this. And so you're probably wondering why these numbers are different. And it's to do with this equation. So the difference in mass has actually been changed into energy, because inside the nucleus you've got protons and neutrons. The protons all have a positive charge, so they're repelling each other, and they're held together by the neutrons. You can think of the neutrons as the glue that keep the nucleus together. And how they do that is through strong nuclear force, which involves quark interaction between neutrons and protons. So the energy that's needed to keep the nucleus together comes from the difference in mass here between what you actually would expect it to be and what it actually is in reality. So you need a certain amount of energy to keep the nucleus together, mainly because the protons all have a positive charge, so they all repel each other. So you need energy to do that, and it comes from here, this difference in mass. Okay, so let's go back to nuclear fission. Nuclear fission is used in atomic energy, used in nuclear power plants, and a huge amount of energy is given out. And in the second video in this series we'll look at fusion, which is not really a good option as a power source, which we'll get to later, but fission is actually much more preferable. And mainly because a huge amount of energy is given out in the chemical reaction of fission, which is this, which I'll talk about in a second. A huge amount of energy is given out. So I'm going to put red around this just to demonstrate exactly how much is given out. So a huge amount of energy, and it's actually 10 million times more energetic than burning methane. So if you took equal amounts of uranium 235, an equal amount of methane, which is natural gas, and you measure the amount of energy given out, the uranium 235 would be roughly 10 million times more energetic. So as far as options for a power source, it's very favourable. So that's a little check in the pro column. Check in the con column is that it's very dangerous, and you need to mine it from somewhere, so it's expensive to do that, but it does have pros and cons. Okay, so the idea of fission, this nucleus will decay at a very slow rate. I think uranium-235 is actually millions of years, if not billions of years, but the half-life for it. But you start fission, the splitting of the nucleus, into two smaller nuclei by hitting it with a proton. A neutron. So you take a neutron and you fire it at this nucleus. Then what's actually created is a very unstable version of uranium. Still uranium's got the same atomic number, but the mass number went up by 1 because you got one extra neutron. So this is very unstable. So what happens to this is that it breaks apart into these two nuclei. So this is krypton, and I've got my symbol wrong there, but element number 56. I'm not sure what it is right now, but it's not barium. No. So you got two smaller nuclei here. But the big benefit of this type of energy is you get the neutrons produced again. So you fire one neutron at this element, and in the chemical reaction, or the nuclear reaction, you actually get 3 more neutrons produced. And also this huge amount of energy given out. So in a nuclear power plant, that energy is then it's converted to heat, or it's controlled heat. So that energy heats water, which turns into steam, which then drives turbines, which then produces electricity. But it's a huge amount of energy given out. And the nice thing is you get more neutrons produced, so you don't have to keep generating more neutrons, because these neutrons will actually collide with more uranium nuclei. So this is a definition of a chain reaction. So as more neutrons are needed for more reaction, the reaction produces them. So you get 2 stable nuclei, which are obviously, these 2 numbers make up 92. But then you get more neutrons produced, and then this huge amount of energy. But the nice thing is these neutrons will go back, react with more uranium, and then the chain reaction starts. So, but a huge amount of energy given out. 10 million times more powerful than burning methane. There are only 2 elements that can, or isotopes, sorry, that can undergo fission. Uranium-235 is one, and then plutonium, Pu, smelliest element ever, 239. So these 2 are the only options you have for fission. And I think that's it. Yeah, so just to recap, the energy in the nucleus comes from the change in mass from what you calculate the mass to be to what the difference between the calculated and the actual measured mass. That mass is converted to energy through Einstein's equation. Energy and mass have a relationship. And the nice thing about this is that a small change in mass results in a huge amount of energy. And the reason for that is because the speed of light is equal to 3 times 10 to the power 8. So if you square that number, even if this change in mass is really, really tiny, and in this case it is, then there's a huge amount of energy given out. Or actually, compared to the amount of mass that you had, or the change in mass, the amount of energy that's given out is much, much bigger, because you're multiplying it by, well, that'll be very roughly 10 to the 16, so that's a huge number. You multiply it by this small number, you get more mass. So, the nice thing about fission is that the neutron that you need to start the nuclear reaction, you actually get 3 neutrons produced for every 1 neutron that you need, so cost effective, huge amount of energy given out, way more powerful than any other anything we've found so far. There are only 2 elements that can undergo fission, and Nate, is that it? All right.